Greetings everyone, welcome back. Professor Simon here for a little side topic so that we can build up for the next big topic. We need to talk for a moment about being able to divide polynomials, and this isn't a topic that comes up all of the time, so I want to put a generic method here that works really well for speed and accuracy, so that you have something to hold on to and move on with if you want. Okay. Now, bottom line, if you already know how to divide polynomials, or if you think you can practice and get it, then you don't actually have to look at what I'm doing here. Skip to the end and look for the integrals that I give as an example that this is used for. If you want a more basic version, go over to my college algebra in the polynomial section in the playlist for college algebra, and you'll find that I also teach basic synthetic division there as a sort of a starter. Okay, so for this one, I'm going to expect that you already kind of know a little bit of synthetic, and I'm going to jump right in, and we're going to generalize synthetic so that you can see it's actually usable for absolutely any polynomial division. Okay, so let's jump right in for this one right here. I'm going to do these two divisions by synthetic division. Synthetic division is when you want to use just the numbers in the structure and not have to keep rewriting the variables all of the time. And really, the trick to synthetic division is bookkeeping, just making sure you're keeping track of where all of your place values are, and making sure that you don't lose your spot in the progression. So for this particular setup right here, what I do is I take whatever the denominator has to offer and I change the sign on it. So in this case, that would be -6, and I call it putting it in the box. So this is the thing that I'm dividing by, and then the coefficients of the numerator line the top. So in this case, it would be 3, 0, 5, and -4. I'm going to draw a line here. Now, real quick, where did that 0 come from? Don't forget that I need to make sure and accommodate every place value of x all the way down to the constant term, right? So you should be able to count the powers, 3, 2, 1, none. When you're doing these divisions, you should count the powers of x down. Okay, now in some instances, people like to just say bring the 3 down or do whatever. I prefer to throw in a 0, and basically what's happening here is whenever you divide, you have a shift in your place values, right? So in other words, I'm doing x to the 3 divided by x to the 1, so the answer is going to shift to x squared, and so all of my values have to go in that light. What you do is you add a column in order to get the current answer. So 3 plus 0 is 3. Then you use a multiplication of the number in the box to get the next column. So -6 times 3 is -18. And then I can keep going. I can add and multiply, add and multiply. So I add here, I get -18. -6 times -18 is 108. I add 5 to 108. And I get 113. Then I do -6 times 113, and I get 678 negative, like so. Then I add these two together, and I get -682. Then the rest of this kind of division here is soaked up in interpreting the answer. Okay? Now, however many values of x you have in the denominator, in this case x to the 1, right? However many powers of x you have, x to the 1 in this case, that's how many remainder spots you should anticipate. So in other words, this spot right here is a remainder. That means from here on out are the normal whole parts of the answer. So that means that this would be the number portion, this would be x to the 1, and this would be x to the 2. And remember, that makes sense because I started with x cubed and I'm dividing by x, so I should be ending up with just an x squared term. So then the answer to my division here is this division is equal to x squared times 3, right? 3x squared minus 18x plus 113. Then minus 682 over x plus 6. And that would be the solution to that division. All right? So just imagine if you had to integrate this particular fraction here. It would be very daunting to have to integrate it in that format of that fraction. However, if you notice that a power in the numerator is bigger than the power in the denominator, the degree, the overall power, then that means you can do this division. So when you do the division, notice an integral would be split up into these 4 pieces. And each one of those should be a piece that you would recognize how to do the antiderivative of. 3 power rules and then a logarithm rule. Okay, let's do another example here. So with this one, it's a little bit different because you'll notice I have the 4 here next to the x. In my earlier lectures, to make things easier for structure and for the college algebra, I went ahead and just fixed it right here. But there's actually a more generic structure that can help you get through this and more generalized pieces a little bit more organized. It's just a little bit more bookkeeping to keep track of. All right, so here's what I'm going to do. I'm going to still take my pieces from the numerator here, 4, -5, and -10, and I'm still going to put a number in the box here that reflects the opposite of this. So in this case, -7. However, I also want to consider that I should have wanted to have just 1 times x, like over here. So right beneath this, right here, I'm going to put divided by 4. And then I'm going to draw an extra line. Okay? Because what's going to happen is I'm going to do the normal synthetic division like here, but then I have to remember that the whole number parts, now just the whole parts, not the remainder part, just the whole parts, need to be divided by 4 in order to make this correctly balanced. Now, why not the remaining part? Because the remainder part goes over the original divisor. So it actually would have a 4 over 4, which balances it out anyway. So you only do this division by 4 rule on the whole number parts. Well, okay, so since I need to figure out where my remainder number is going to be so I know when to stop dividing by 4. I look at my x to the 1 here. That means I'll have 1 spot for the remainder here. Right? So this spot right here will be the remainder. That means I'm going to draw myself an imaginary boundary here. Stop dividing by 4 when you get to that wall. Okay? So just like before, I'm going to put my 0 here because that's my displacement. Now I add. So 4 plus 0 is 4. And then I divide. 4 divided by 4 is 1. Now I come back like I did before and I do my multiplication. 1 times -7 is -7. I add. That's -12. Divide by 4, and that gives me -3. -3 times -7 gives me 21. I add to get 11. But that's in the remainder spot, so I don't do the division there. All right? So let's write out what the answer is to this now. I have the remainder, I have a number, and I have x. So that means the answer to this is just x minus 3 plus 11 over 4x plus 7. All right? The other key to remember here, because we're about to generalize this for synthetic divisions that you probably haven't seen before. Okay, this is normal synthetic division. The key to remember is the diagonal bit here. Every time I do a multiplication, I always multiply and give answers in diagonals. Right? Every time I get an answer, I'm going to multiply and it goes in a diagonal from there. That's important for the way synthetic division displaces everything. It works in diagonals when you're setting up the new rows after your multiplications. All right? Now let's expand your horizons on synthetic division. If you were taught synthetic division before, you probably were told that synthetic division can only be done on divisions that have a linear denominator, typically a linear binomial. So notice here I've got non-linear denominators, x squared and x squared here. Okay? So typically these don't work with the traditional synthetic division lesson because they only use one box. If you layer your synthetic divisions appropriately, it works just the same and just as quickly and much more efficiently than a long division. So let me work this one first. I have x cubed plus x plus 2 divided by x squared plus 2x minus 8. So again, I'm going to write my numbers from the numerator, which in this case are 1, 0, 1, and 2. Remember, I've got to account for all of the powers of x starting at the top. So 3, 2, 1, none. Right? Okay. Now along the side here, I need 2 boxes. So remember, before I had 1 box, right? Now I'm using 2 boxes. And notice that my number in front of the x squared is 1, so I don't have to do one of those division rules yet. Okay? So now I'm going to put the numbers in the box that are appropriate for the division. And you always want to count upwards with this one. You want to go up the side. It just makes the structure of the diagonals more natural from where you're used to with the other synthetic. All right, so here I'm counting the x squared as the bottom here, like the 1. If I had a division rule, it would go there. But I don't. So I'm going to keep going here. So it would be negative 2, because remember, you're doing the opposite. And then plus 8, again, because you're doing the opposite. And don't forget, the reason you're doing the opposite is because with division, every time you do a level, right, you subtract and move on. And that's what we're basically doing by changing the signs. We're subtracting by changing the signs. Okay, so just like before, you have your shift, right? In this case, since I have 2 levels, I have to do 2 levels of shifting. And they work in diagonals. So before, it would have been like this with a single 0, and you see how that works in a diagonal. So what would the next diagonal be? It would be like this. So again, this is just the natural zeros, or for some people, they just like to drop the number, whatever. This is the natural setup. This is not actually in the division there. This is the setup of what's happening when you divide. That's the shifting of the place values. Okay? So now I do my columns. You add. 1 plus 0 is 1. Okay? Now remember, everything works in diagonals. Okay? So if I multiply this 1 by the numbers in my box, it should work in a diagonal format like this. It should work in a diagonal. And it does. Notice I've already filled in these values, right? So if I do 1 times negative 2, what's the first spot it can land in? 1 times negative 2 is right here, negative 2. And then 1 times 8, where's the first spot it can land? Right here. Notice I do not have this column completed yet, but I do have this one. So I continue. 0 plus negative 2 is negative 2. and then I've got my next value. And remember, diagonal, right? It's going to go this way. So for the visual here, let me go ahead and draw it in. It's going to go like this. -2 times -2 is 4. And -2 times 8 is -16. Okay, now here's the thing. Once I finish all of the top row like this, then you don't need to do any more multiplications, okay? And then I'm going to do what we call another shift. See this 0 here? This 0 is here for the same reason that these zeros are here. Here's another way that you know that you're done. Remember, the highest power in the bottom is how many spots you can expect for remainder, right? So 2 remainder spots. That means both of these locations, right, here, this is 2 different columns. Both of these should be remainder. Okay? Think about that for a second. You can have a remainder that has an x in it now because the remainder just has to be a lower power than this x squared. So the remainder fraction that I write, you could expect to have an x and a number, and that's what's happening here. The remainder spots, there should be 2 of them now. Okay, well, I can just add up my 2 columns now and finish that out. 1 plus 8 plus 4 is 13, and 2 minus 16 is -14, like so. So then this division right here, the answer to it is going to be x minus 2. See, that's here, past the remainder, number, then x, right? And that should make sense because x to the 3 divided by x to the 2 should give me an x. Plus, and then this is my remainder portion. That's going to be 13x minus 14 over the original divisor, x squared plus 2x minus 8. Okay? All right, let's do it again. For this guy right here, 5x to the 4th plus 4x cubed plus 7x squared plus 8x all over x squared plus 2. And this one's slightly different because the denominator is missing the x power, right? So I'm going to go ahead and set up my coefficients here. I have 5, 4, 7, 8. But remember, I have to do all of the powers, even the constant. So I actually have one more. I have a 0 there. It should count down, right? 4, 3, 2, 1, none. Since this is x squared, I should expect 2 boxes. So I draw my line, right? And I separate it. So I have 2 boxes. Okay, I would put my little division rule here if I needed one, but there's just a 1 in front of the x squared here, so I don't need the division here. I'm going to start counting in order, right? Now, real quick, don't forget, this x squared plus 2 technically is x squared plus 0x plus 2. So when I'm filling in my box values here, the first one that I have to put is 0. Then I move up and -2. Okay? Just like before, since I have 2 boxes, I should expect 2 diagonals of shift here. That means I should have a 0, that's 1 diagonal, and then I should have a 0, 0, that's another diagonal of shift. Right? And also, just like before, I mean, you'd eventually see this later, but the last one's going to be shifted in like this. Okay? So I've got the 2 diagonals again, here and here. Oh, I'm sorry, 3 diagonals, here, here, and here. Right? Because you have to finish the whole top row. You have 3 diagonals here. But I still only have 2 remainder spots right here. These 2 columns are going to be remainders. And I know that because of the denominator x squared. Okay, so let's do our division here. I add my column, I get 5. 5 times 0 is 0. 5 times negative 2 is negative 10. I add this column, I get 4. 4 times 0 is 0. 4 times negative 2 is negative 8. I add this column, I get negative 3. Negative 3 times 0 is 0. Negative 3 times negative 2 is 6. So 8 minus 8 is 0. And 0 plus 6 plus 0 is 6. Okay, so then let's write out the answer here. So then this division is equal to, now these are both remainders, right? So number x, x squared. And the x squared should make sense, right? 4 minus 2 is 2. So this should be equal to 5x squared plus 4x minus 3 plus, now I don't have an x term, but I do have a 6, because this would be x and number, right? Just like before. You have to do all of the powers less than the thing you're dividing by. So what I have is 6 over the original divisor, x squared plus 2. So now let's get a couple of examples that use not only the higher exponents in the denominator, but also the division rule that may come along with it. And that's pretty much the generalized version of using synthetic for any division, any polynomial division, right? So here I've got 12x cubed minus x divided by 4x squared plus 1. Alrighty. So then when I do this division, I notice there's a lot of powers missing. So I'll keep that in mind when I'm writing this down. I have to do 12, that's the cube. Then squared is 0. Negative 1 is the linear. And 0 is the constant. I've got an x squared in the denominator. So I'm expecting 2 boxes. So I'll draw my line about right here. I've got 2 boxes. But I also notice that my leading coefficient of the bottom is not 1. Therefore, I need a division rule, division by 4 in this case. And remember, that only counts for the whole number portions. So I need to be able to anticipate where the remainders are going to be so that I know when to stop dividing. Okay, so since I have a squared here, I'm expecting 2 columns of remainder. Okay, so that means I'm going to have an imaginary little split right here of where I'm going to stop dividing. All right, so then let me level that out a bit. I'm noticing that it's 4x squared plus 0x plus 1. So 4x squared, I've got the 0x and then minus 1. I have 2 levels of displacement, right? So 2 diagonals. Here's one diagonal, and then here's a second diagonal, like so. I'm going to add, so I have 12 here. 12 divided by 4 is 3. And don't forget, you're multiplying this number, the 3, but it's working along the diagonal that's with the 12, okay? So 3 times 0 is 0. 3 times negative 1 is negative 3. Add up this column, I get 0, which divided by 4 is still 0. 0 times 0 is 0. 0 times negative 1 is 0. And that was the last diagonal because I finished the top. So I technically have a little bit of shift here. Let's add up this. I get negative 4 and 0. So let's see, what do I get from this division here? I just have a 3 and no number, so that's 3x. And then I've got negative 4 over the original divisor here. Okay, so I've got that this is equal to 3x plus negative 4x over 4x squared plus 1, like that. Okay? Now, I picked a larger one here just so that you could get the grand scale of it here. Get a generic one. Okay, 5, 4, 3, 2, 1, none, not missing any places. 3, 2, 1, 0, not missing any places. So let's go ahead and set it all up. I'm going to have a 3, a 17, a 7, a 17, a 13, and a 6. This is cubed, so I should anticipate 3 boxes, and I'm going to need a division rule. So I'll just draw a big old line here. I need 3 boxes. 1, 2, and then 3. And then I also have a division by 3 rule. And I should have 3 remainder spots. So these 3 columns here, this is where the division rule should cut out. These 3 are going to be the remainder spots here. Okay, now what goes in my division here? I'm going to go in order. So negative 2, negative 3, negative 2. Right, because it's 2, 3, 2. So negative 2, negative 3, negative 2. I have 3 diagonals of shift, right, because of the cube. So that's 1 diagonal. Here's 2 diagonals. And here's 3 diagonals of shift. And it should always complete out that first column, because the first column is always your drop column, right? So 3 plus 0 is 3. 3 divided by 3 is 1. Now I use the 1. 1 times negative 2 is negative 2. 1 times negative 3 is negative 3. 1 times negative 2 is negative 2. When I add up this column, 17 minus 2 is 15. Divided by 3 is 5. Now I multiply. 5 times negative 2 is negative 10. 5 times negative 3 is negative 15. 5 times negative 2 is negative 10. Okay, I can add up this column, and that gives me negative 6. Divide by 3, I get negative 2. Okay, now I've hit the remainder wall, so I won't be using the division rule anymore. These last 3 spots are remainders. I do need to do one more multiplication here, and then I need to fill in with the shift zeros. So negative 2 times negative 2 is 4. Negative 2 times negative 3 is 6. And negative 2 times negative 2 is 4. Notice my last diagonal is complete because I hit the end of the top. And that's when the rest of it should shift in. Right? 2 diagonals of shift there. And then I just complete up my last 3 rows. So I've got 17 minus 17 plus 4. So I'm just going to get 4 there. Then I have 3 plus 6 is 9. And 6 plus 4 is 10. So let's interpret the answers here. These last 3 columns are the remainder, and that should make sense because that would be number x and x squared, and it needs to be anything less than the cube. So it goes up to squared, makes sense. Then this would be number x and x squared, also makes sense because 5 minus 3 is 2, so it should go up to squared. Okay? So, answer here. This is equal to, this division is equal to x squared plus 5x minus 2, that's this, x squared, 5x minus 2, plus, now I have to do the fractional part. That's going to be 4x squared plus 9x plus 10 over 3x cubed plus 2x squared plus 3x plus 2. And there's my division quotient answer. Okay? To finish up, let me show you 3 examples using the divisions that we've already discussed here in this lecture with a Calc 2 spin on it, and that is how to do these integrals. If I want to integrate this particular rational function, the first thing I notice is that the degree of the numerator is more than the degree than the denominator. By the way, equal always also works. You can divide when the 2 degrees are equal. You should expect a whole number plus some remainder. Then from here, once you do the division, notice that the integral can split up amongst all of the different pieces. That makes it incredibly easier. These 3 are just power rules, and then this right here I hope you recognize as an arctan rule. So then right here I'm going to have 5 over 3 x cubed after I do my power rule plus 2x squared minus 3x. And then right here, the 6 is not part of that, so I'll have to do 6 and then times the arctangent, right? Now the x is the thing as my variable, and 2 is my a squared. So I should have over square root of 2 and over square root of 2 for that one, plus c, right? So then I was easily able to do the antiderivative of this complicated fraction just by performing a division and then following through on individual antiderivatives. Same thing here, right? If I do this division, it becomes 2 separate, much simpler objects. Antiderivative here is just going to be that power rule, so I'll have 3 over 2x squared. Here, though, I need to go ahead and rewrite this and possibly do a u substitution, right? I'll go ahead and put the minus out here. And the derivative of this piece right here, if I'm going to do a u substitution, right? So let's say I let u equal 4x squared plus 1. Then du is going to be 8x dx, right? I have 4x dx, but I need 8x dx. So to make that work, I'm going to do times 1/2 integral 8x dx over 4x squared plus 1, which I hope you'll notice is just going to be the integral. This is just 1/2 the integral of du over u, which is going to give me 1/2 of the ln of the absolute value of u. Okay, so these are the substitution steps that I'll be taking there. So then my final answer should look like this: 3 over 2x squared minus the 1/2 ln absolute value of 4x squared plus 1, which was my u, right, plus c. Okay. Very similar over here. I've got my power rules for this guy. So 1/2 x squared minus 3x. And then again, this is going to be a logarithm substitution. The derivative of the inside is 4. So I need to pull the 11 out, so that'll be times 11. And I need to have a 4 dx to do this substitution, right? Let me go ahead and write out the steps. If I let u equal 4x minus 7, then du is just 4 dx. So to get that 4 dx, I'm going to divide by 4 on the outside and multiply on the inside like this. So notice I've got the du over u again, which is going to give me the ln antiderivative. So I've got 1/2 x squared minus 3x minus 11/4 ln of 4x minus 7 plus c. Okay? So I hope this little brief lecture series has helped you see how division can be useful with calculus, and just being able to do the division in general for all of the different types.